I'm doing my PhD at Hong Kong University of Science and Technology. And in this session, I will talk about an optimal algorithm that helps you to produce optimal blocks. So in another word, it basically means that no matter network parameters, right, like the block size that Marcus talked about, when you know your network parameters, this algorithm helps you to improve your revenues, no matter what. Of course, it always comes with a cost, but the good thing about this algorithm is that because it's polynomial, it will be within 1 second of Cardano block time slot. This is a joint work with Cardano Foundation, my colleagues Takjan, Amir, and Sergey, and of course from Cardano, it's Marcus, who his project helped us to capture snapshots of transaction pools. Please feel free to stop me whenever you have a question. Here, I will not go through into the details for the algorithm. And I just want to show you, whenever you have these optimization problems, how you can exploit the sparsity in the real world data so you can solve a very hard problem very fast, right, practically. Okay, in this presentation, I will go through motivation, problem definition, and at the end, I will talk about experiments, right, and how much we improve the current situation in Cardano. So, okay, everyone in this room knows about producers and miners. Basically, in every blockchain, we have this entity who is in charge of creating the next block. This entity can be elected like proof of stakes consensus models, or it can be when they solve a hash puzzle. But no matter what, this entity needs to, we need an entity or a role to create the next block. So this role, they usually go through a mining step, or in case of Cardano, I guess producing a step, which basically means they need to keep a track the state of the blockchain, and they need to pick a subset of transactions to put in the next block if it's their turn or if they have solved the hash puzzle. But this is a very computationally heavy thing to do, right? They need to keep track the blockchain state, they need to verify transactions, they need to execute smart contracts, and they also need to go to like the problems that Marcus talked about, the propagation in the network. So they have to do a lot of work. So we need to give them an incentive to do. This usually goes as like mining rewards or block production rewards. In Cardano, like Bitcoin or Ethereum, we have 2 types of rewards. The first one is monetary expansion, which basically means depends on protocol rules you will get and reward if you are a miner. So if you put a stake, you will share a reward. Usually, block producers, they don't have that much control on this part. It is predefined based on the network or based on the protocol. But there is also a transaction fees, which is paid by users, right? So users usually pay miners or block producers to first verify their transaction, and then they put their transaction into the blockchain, right? So basically, they are paying for the efforts. Block producers, they have a control over transaction fees, right? Because they are the people who pick what transaction should be in the next block, right? So basically, if they can maximize these transaction fees, they can maximize their revenues, right? And we was interested in this problem in Cardano for basically two main reasons. First, Cardano has a 1 second block interval, which makes everything very challenging, right, compared to Bitcoin even or Ethereum, right? For Bitcoin, you have 10 minutes, so you can afford to not be very efficient. But in Cardano, you cannot do that. So, and the second thing, Cardano can execute complex smart contracts, right, which shows that this type of modeling for creating optimal blocks can work even if you have smart contracts, not just when you have simple transfers. And okay, so the objective, as I said, we want to maximize transaction fees or maximize miners' revenue. And our approach is we want to exploit the sparsity in the relationship between transactions, which usually is there in the real world scenarios. We have done this even when we are doing program analysis, right? Even this sparsity happened when you write a program. We did an experiment with the help of Marcus, who's not here. And we did a 50-day, and we found that we can improve or increase the transaction fee revenues by $1,300 per day, which is quite a lot if you see it in a year. Of course, we didn't do a yearly experiments, but it will be around that or of half a million improvement, which is interesting because this data is already there, and because block producers to use some heuristics, they cannot get this money, right? So it's like, again, this improvement is interesting because you can almost get it with implementing the algorithm, right? Okay, let's go. So let's do a problem definition. In this problem, we care about 3 constraints in the block Cardano. First, transaction, they have dependencies. Transaction have conflicts, which I'll talk about it a bit later. And of course, you have block size limits, right? So you need to pick, if you are a block producer, you need to pick a subset of transactions and put it in your block. And the total size of this transaction should be less than this block size limit. So you have some constraint that you need to follow, right, to have a valid block. And so the problem will be given a block size limit and given a finite set of unmined Cardano transactions, right? Let's say you have your snapshot of your pool. Then we want to find an optimal block, which the size constraint is fulfilled. All the dependencies and conflicts are there. And you get the maximal transaction fee. And you can prove, right, you cannot do better than this. That is really interesting about this algorithm. It is guaranteed, right, theoretically guaranteed that you cannot do better than this. So let's about, I'm pretty sure everyone's familiar with these concepts, but just go through them very fast. We have dependency conflicts in UTXO-based model, so which means that if you want to put this transaction in your block, you need to make sure the first transaction is already on the blockchain, or you will also put it on your block. And this dependency happens when an input in the new transaction is spending an output from another transaction. The second constraint is conflicts, which is basically 2 transactions will have conflict if they are trying to spend the same output, or another word, double spending problem, which was solved originally in Bitcoin. So if you are creating your block, right, you cannot put both T2 and T3 in your block. You need to do T2 and T3. And this is a nice example because it also shows that T3 it's also depend on T1 and T2 depend on T1. So this shows that this can get out of hand, right, because you need to follow all these constraints. And you can have multiple constraints within one block, right? All the conflicts and dependencies. We need to model this, right? Because we want to reason about this formally. Of course, we model it with graphs. We are computer scientists. We put one vertex per transaction, and whenever they are depend on each other, we put on direct edge. This means that transaction 6 depends on transaction 1. Or transaction 2, it depends on both transaction 3 and transaction 5. And then we put an indirect edge for conflicts, which basically means that you cannot put transaction 1 and transaction 3 in your block at the same time. And then we have our dependency conflict graph. So with this graph, we can model our conflicts and dependencies in the blockchain. This is already nice, right? So we have a formal way to model this. Now, second, we want to create an optimal block based on our constraint, right? Based on this graph. So if you want to solve this problem directly, it's very hard to solve it, right? No tool exists that can do this. You have some heuristics which already using which we are already using in producer nodes, right? But you can never have a guarantee, right? That actually I'm getting the best block that I can get. What we like to do in our group is say, okay, I define a sparsity parameter. Here we will talk about three decompositions, three depths decomposition, or intuitively, three decomposition shows that how star-like your real-world conflicts and dependencies are. And then we use some, some tools, right, that they are practical to find these decompositions. This part is still hard to do, but because they are solving just this problem, they are very efficient. And then try to create a polytime algorithm on size of transactions and the block size. So provably, we can get an optimal block, right, if we have this three decomposition, right? Three depths decomposition, which is very nice, right? So basically, in our work, which was published, we found a new way to do this part, right? This is really hard, no one can do this. This is already some practical and efficient tools that they can do this. So we create an algorithm, or another word, a dynamic programming, on three depths decomposition of our dependency conflict graph, which resulted very nice. Okay, let's a little bit talk about three depths decomposition. Again, here I'm giving you an intuition behind the sparsity parameters, right? We have many more sparsity parameters. Here we just want to talk about three depths decomposition. So in three depths decomposition, you already have a graph, right? You want to create a tree out of this graph with new edges, right? Which the nodes are the same nodes that you have here, but the edges are new edges, right? But we have a tree here. But what property we are looking for in this tree that it is really interesting for us is that every edge or every conflict or dependency happened in the original graph, it's here in ancestor or descendant of the original node, which is very nice. Why it's very nice? Because it shows us if our tree here is shallow or the depth is small, then when I want to put transaction one in my block, I just need to check the ancestors, right? And this is really fast comparing to checking all the possible solutions. So here it's also another three decomposition, three depths decomposition. We can have many three depths decomposition. Again, the edges should be ancestor or descendants compared to the original graph. And of course, this is run because we have an edge here. No, this is correct. Okay, so let's move on. And we define our sparsity parameter here. We call it three depths. And among all the possible three depths decomposition, the smallest number is we call three depths parameter. So which here is 3 because the depth of the graph is 3. Okay, let's see how I can use this decomposition or this nice tree to solve my very hard problem. How we do it, again, I will not go deep in the algorithm steps, right? I just try to explain how from top view, how does it work. And it should be interesting because when you want to solve another optimization problem using the sparsity parameters, you usually go through these steps. So this is nice to know. So how do you do it? I have my three depths decomposition here. So each edge is a transaction. And I try to solve my problem step by step, and in each step, I add a new node. So here, I will solve my problem if I only have transaction 1. Here, I will solve my problem if I only have transaction 1 and 2. And then again, if I have transaction 1, 2, 3. So these edges, they are coming from the original graph, right? So the red one is conflict and the blue one is dependency. And why I iterate through my solutions like this, because we are doing dynamic programming, right? And whenever I want to solve for tree, I will use my solutions or the optimal blocks with 2 and 1. And this is very nice because it helps us to fix or solve the optimal block when we have a new transaction in our iteration based on the previous solution. So it makes it very fast comparing to go through the everything again. And then we add transaction by 1 until we have all the transaction. And then I add my transaction 7 at the end, because I've already found the optimal block for all the sub-problems that I need to solve. Up to transaction 6, I can use all those solutions to solve for transaction 7. And again, this is nice because we go step by step and we use previous solutions, so we can make it so the final answer will be very fast. And let's see how one step look like, right? Let's say in this step, right, I already found the optimal block for transactions 1, 2, and 3. And now I have transaction 4, which is new. So what I do, right, this is, as I said, every original edge or every conflict or dependency edge that happened in our DCG graph. Here, it should appear between 4 and its ancestors, right? So all the transactions that can affect 4, it's 2 or 1, or all the transactions in the ancestors. So then I will go and check by 1, right? Instead of checking every possible solutions, I only check sub-problems that can actually affect 4. So first is just if I put only 4 in my block, it works, right? Because it should not work, right? Because 4 depends on 2. And because I'm not putting 2 in my block, then this is an invalid transaction. So I will not solve this line anymore. Second, I will check 4 and 2. And this is really nice, right? Because 4 depends on 2, and I'm putting 2 and 4 in my block. So this is a nice subset of problem that I can solve. And then because I've already picked these 2 transactions and I solved everything for previous ones, I can find the answer for picking 4 and 2 based on the previous solutions. Let's check for the next one. Can I put 4 and 1 in my block? No, because they have a conflict. So basically, this means I already discarded and I will not check this subproblem anymore. And the last one is just putting all of them in my block, right? Again, I cannot do this because there's a conflict here. Even though that I'm allowing, even though I'm fine with this dependency, I still cannot do it because 4 and 1, they have a conflict. This is very nice, right? Because if you think about your problem and if you want to find all the conflicts and dependencies, right? Whenever you want to argue about one transaction, you need to go through every transactions. But because we decompose our original graph and now we have a shallow tree, this gives us 2 things. First, a very nice way to implement our algorithm iteratively. And second, it gives us a formal guarantee, right? That because I know that my tree is shallow or the depth is small, I will have a fast algorithm, right? No matter what, and I can improve the revenues. So in another word, when you exploit another sparsity parameters, they also give you these guarantees, right? And that's why we are very interested to them. And we have observed this sparse, I don't know how I can put it, but this sparsity is in every other problems, right? In the user programs, basically everything that humans work with them, they are usually sparse. And these parameters, they help us to formally reason about these sparsities. And in Cardano, you can have an idea, right? Because it's a very big network. People, even when they have transactions, they are usually a subset of people that they are usually like to send transaction to each other's, right? So you will have this sparsity. And this idea, when we use these parameters, it helps us to formally reason, all right, or to prove theoretically that this is optimal. Okay, so this was nice. So we, with the help of Marcus, we evaluated our algorithms on 211,000 blocks. And we found out, yes, the data is sparse, right? The tree depths, how a star like our tree is. It's usually one, right? It's usually people, they don't care about each other, or two or three, or in very rare situation, this y-axis is logarithmic. Or in very rare situations, we end up with a little bit more sparse, less sparse graph, but because our algorithm, it's not, the complexity of algorithm, it's exponential in this number, right? But this number is already small, right, compared to the whole graph. So the algorithm worked very well in practice. And the average tree depth was 1.45. So we run algorithms, our algorithms on all these blocks. And in total, we could improve on 50 days. In total, we could earn or increase the profit of miners by 67,000 US dollar, or per average, per block, $1.21, which is really nice because this data is already there, right? You don't need to reach for a better pool, or you don't need to increase the block size, right? Because these are the input parameters of this program. So basically, when you improve this, you will add a delay your product in your block production. But I think that delay worth it, right, in long time. So, and the delay, I forgot to add it here. Yeah, the delay is on average 0.31 second. So, which is very nice. This is before parallelization. This is kind of nice because it's within 1 second of block intervals, and it can improve your revenue, right, for each block. Okay, so let's do a conclusion. Our algorithm is probably optimal. It's polynomial time. Roughly in year, it can make $500,000 US. And our tool is available on GitHub freely to use. Okay, and I want to talk about a little bit about my research group. We are a research group based in Hong Kong. We like the intersection of parameterized algorithms, program analysis, and blockchain, right? So basically, we like to solve these optimization problems. For us, it's interesting because we can in theory, we can find an optimal algorithm for them. So this is interesting for us. Also, we are an academic group. So basically means that we do it non-profit. Everything will be available open source. And we helped other companies or other blockchains, right? We are working with Ethereum. So we could improve their currently available tools. And we strongly publish in the main or in top tier conferences. And we are kind of international, even though all of us in Hong Kong, we are from all over the world. And that's it. Thank you. Okay, any questions? Yes.
Yeah, a few questions. So for Bitcoin, this makes sense, I understand, because Bitcoin, the miners get the transaction fees. For Cardano, the transaction fees are used to boost the reserves for all pools in Germany. So if you do this in Cardano, you essentially collectively would collect more reserves to pay out more rewards. But I also wondered, have you looked at tiered pricing, tiered fee pricing? There's a proposal for Cardano to implement this later on. Not sure what the stage of development is, but there's the idea that there's no fee auction market, but a tiered model where different priorities can be had, and some transactions are more urgent and have higher fees. If this also has a similar effect like what you propose?
Okay, let's answer them one by one. The first thing, yes, in Cardano, block production, it's happened collectively, right? It's mean in each epoch, we mine transaction, and at the end, we divide these fees. So basically, this algorithm still helps you to improve your fee personally, right? Because you're improving the total, and you get a share of that, right? Depends on your block production. You also help others. I can see that, right? But you will also help yourself. But honestly, the problem that you mentioned, it's already there, right? When it's happened collectively, no matter what you do, it could make sense. Okay, I will just create blocks with minimum transactions, right? Because I don't want to help others, but I don't get help to myself. So my point is that if it's already working, adding this algorithm won't change anything, right? If it's already incentivized miner to make the best block they can get, this algorithm should not change anything, right? Even if the viewpoint is only for one block. We are interested to extend this algorithm, right? So instead of solving it for one block, then we are interested to solve this now. Instead of having one instance, you have one sequence of this instance, right? Because the transaction, they also have this timing. They should happen after this block, before this block, right? And then when you add them, then you will get extra hard, theoretically hard problem to solve. So we are interested to solve that, but that doesn't mean that this will not work, right? This is already working. That will maybe it could make it better. I'm not sure, but this already you can prove, right? This is the best you can do as one block producer in a pool. The second problem is when you have these auctions, right, to put high prioritized transactions, or when, I guess in Ethereum we call this problem NEV, right? People, they are fighting, they are increasing the gas usage, or they bribe miners personally, or the block producers to put their transaction. This happens, right? In this problem, in setting, we assume every transaction, they have equal opportunity, right? They don't have any side deal, or they don't have any action. But even when you have those actions, right, it means that you will have a set of transactions that they are willing to pay you more. They are willing to compete with other transactions. You still need to pick subset of winner transactions, right? So this algorithm still will be helpful there, right? Because even you have, let's say we have an auction, we have 10 winners, but we cannot put all of them because you have block size limits, right? You need to pick 6, you need to pick 4. This algorithm help you to pick the best 4, the best 6, right? So basically, this will always, in my idea, always will help you if you can spend the time you need, or the additional computational effort, right, on your node. This will always help you to improve your revenue, right? No matter what, you will never suffer from anything. It's not like we are comparing different heuristics.
Yeah, they are doing research for layers and so, and there will just be more blocks.
Yes.
But there is no competition between the transactions, like in Ethereum, that the highest fee gets first. That's not.
Yeah, but it's just when you look at this problem, let's say you increase the size of unmined transactions, right? So you are physically you should not be capable to put all of them in your epoch, right? And they will expire. So at some point you need to pick a subset, right? At some point you need to pick a block, because we will also face this in our data, right? We face this in our data, right? Some of the pools, they were smaller than a block. So basically you could put everything, as you said, in the block. But some pools, that wasn't the case, right? The transactions were close to get expired, or they were twice or 3 times the size of the pool, right? So at some point you need to pick a subset, even if you are not facing it. And even for the auction part, I guess you can design an auction in a way that only enough transactions get picked, right? The highest 5. But I think even then, it might be this solution might be useful.
Yeah, I thank you for the presentation. I have a question similar in vein to the previous ones, because, and my question is, perhaps it starts from a different point of view, which is, You were mentioning that you can optimize the set of transactions because you want to, with these two graphs, the dependency graph and the conflict graph. But in order to do that, you need the transactions within the mempool that exactly are in conflict with each other or that they are depending on each other. And this is why you need to optimize them.
Yes.
And you claimed later that there were these 50,000 transactions, whatever, something like this, in which you improve, or blocks in which you were improving the blocks. Are you saying that at every point in time in the mempool there are constantly transactions that are depending from each other, that are conflicting from each other in the mempool? Because if I look into, in Cardano Scan, if I look into the transactions that are inside of each block, there are something like 10 transactions per block on average. And therefore, or 20, whatever. And therefore, the block is completely underused. So you are able to process all the transactions in Cardano as far as I can understand. Perhaps I'm missing something, but I do not see how these graphs are actually meaningful given the traffic of transactions that we have in Cardano.
Okay, so let me answer the question in two parts. Okay, first, what is the point of the graph, right? If you don't see that much dependency or conflict in the blocks. When we say the 3 depths was 3, right? It means that between 3 transactions, we had conflict and dependency. Of course, we will not see the conflicts in the blocks, right? Because we cannot put them, right? But we actually first observe it in the data that Marcus provided, right? That, for example, I don't know, around 10 block, they had, it's like a cluster of 4 transactions that they were either dependent on each other or they had this conflict, right? We couldn't put both of them. So we observe it in the pool. And the point of the second question, right? You said we need to maintain this graph, right? So basically in this graph for each transaction, right, each edge is either conflict or dependency. So we need this graph because we need to pick a subset of transactions to put it in our block, right?
No, my question was different. Was typically which is the density of the graph that you see? Are there so many interdependencies? How often do they?
No. There are not that many, right? But it's just, I think when we were checking our data, right, out of 200,000, around 50,000, that they had, the pools were big enough. So we needed to pick a subset. And they had a few conflict and dependencies that we needed to take them into consideration. And it's just, even though maybe this right now, this doesn't make sense that much, but this is kind of nice, right? Because if this sparsity continues, if the network grows bigger, if we have more transaction, if we increase the throughput, this algorithm will not increase based on the number of transactions. It has linear dependency. Sorry, it has linear dependency on the size of the pool. But the exponential ones, which usually get if you want to calculate all the possible solutions, it depends on the sparsity, right? So if the number of transactions increases, these numbers should stay low.
One other question, regardless of if it's useful for Cardano right now or not, but maybe in the future it is. I'm just wondering, you said 0.3 seconds is the additional delay to do this. Is this completely CPU bound? Is this already run on a high spec CPU, or is there a possibility to get this down further? Because 0.3 is quite big when we looked at the prior presentation from Marcus.
Yes.
And so assume the algorithm we have now right now is already optimized, as you said. It's not much more to get out of the algorithm itself, but you need more.
No, I think there is there is still things to do, right?
Okay.
Because first you can make the algorithm online. We didn't do it, so it means that you don't need to create this dependency graph from scratch every time. Every time you see a block, you can update it, and that update will make it a lot faster. And I guess depends on the CPU, you can parallelize it a little bit, right? Which also, it could increase it, right? Because as I said, in every step, whenever you check every subset, they don't affect each other. So you can check either of these four instances in parallel. Again, you need to put more CPUs, but the idea is that the network will, or even at this point, is big enough so you get compensated for that because you will get more in terms of transaction fees.
And would you personally say this is ready for production, what you have right now? Would you recommend SBOs to run it?
So we
Just
did
curious.
this code. We did this code for blockchain, and I think it's already in every nodes because we checked our algorithm after 2 years, and now every block is optimal, right? We cannot beat anyone. This case, the core of this algorithm, right? If let's say you have your snapshot when we were checking Cardano node, right? It's just so the good thing about DP programs, they are very easy to implement. And actually, I was looking forward to talk with Marcus or anyone who is interested here. Because we are academic, right? We don't benefit from this one. But we like to see our algorithm implemented in real world situations, right? I know that we are a theoretical group, but our algorithms have been used anywhere. Not anywhere, but in some products. So we can try it, of course, right? And I didn't hide anything, right, to tell you, oh no, there is a catch or there is a niche that, because we don't have it in the real world. Again, the code is pretty simple, right? I just read a set of transactions and do 2 loops, and then I'm done, right? Because the nice thing about Cardano, because it uses extended UTXO model, right? So we are solving the same problem for Ethereum, but in Ethereum, you need to execute different orders, right? Or to have the real gas usage. Here, we don't have that problem. That's why I think it should. I worked in a company for 5 years, and whenever we said it's easy to implement, we end up facing different struggles. And I guess this will be the same way, especially because we have so many instances for each node, right? So it should be very careful. But the good thing, again, about the algorithm, it should be easy to integrate to the tool. And even ourselves, we were looking to see if we can do it or we can connect a community that they are developing the tool to implement this. Because, okay.
So if I understood correctly, even though we in Cardano as block producer do not compete with each other for the highest fees, is in our collective best interest to maximize the fees collected from the transaction that eventually get into blocks and minimize the potential fees which are lost on the transaction that do not go into blocks.
Yes.
And that amount that you showed related to around $500,000, it's a potential improvement for all of block producers, yes, which will distribute eventually to all of us. I just wanted to validate my understanding of your.
Yes.
And the question is
per person, of course.
Yeah, the question is. I'm not sure if you are familiar with the CIP on Cardano related to validation zones, where this graph, dependencies graph, changes a bit with transactions that besides inputs and outputs will have some dependencies, some
like data dependencies,
yes,
right?
yes.
If I remember correctly.
And the question is if this algorithm will eventually can be adapted for this validation zones.
Actually, we model all of these constraints as exactly these 2 edges. So if it was a data dependency, I guess if I remember correctly, it was when I'm using someone else's code or if I'm referencing to someone else, right? Yeah. That here model as dependency, right? Great. So it's already there.
And I think that I'm not sure that I understood correctly. What you are finding is the global optimum or a local optimum of the, let's say, mempool set?
So, okay. It depends on these 2 given, right? You have your block size series and you have a view of your transactions. Yeah. Of course, we are in decentralized network. This view can be different, right? Marcus talked about it. True. Let's say this view is fixed for everyone, then it's a global, right? Okay. But because this view is different, then depends on this view you're improving. It might be the case that you miss some transaction. Actually, we found these instances in both Cardano and Bitcoin. There were some transactions that we didn't see them in any pools or any transaction pool. Someone was keeping them to themselves to put it in their block. So if I don't know about a transaction, I cannot use it to maximize.
Thank you for your answers.
Sure.
And another question, could we integrate this algorithm in the actual code of the node?
I discussed it a little bit. Okay, in my mind you can, because the part that actually this algorithm works, right? It should be pretty simple, right? Let's say you have these two, you have a function that you have these two, then it should be possible to use a couple of functions to implement this algorithm, because it's dynamic, right? You're just filling an array, you are going forward. And okay, maybe I should did a little bit because I'm not sure. So it just whenever you have dynamic programmings, right? It means, hopefully you all remember from our undergraduate time, it means you fill an array iteratively, right? That's why these numbers are pretty nice. That's why it's fast, kind of. So it should be okay, but I'm not giving any 100% sure answer because okay, I'm sorry, but unseen stuff always happen. Even when we were working, right? When we started working, we weren't that familiar with the Cardano. So actually, we didn't know about this data dependency. And then we found in our blocks, oh, there is a thing that is not spending an output, but is still dependable and depends on the area or protocol you use. It's either should be there or not should be there, right? So I guess in development community, we always say things can happen. Things is a nice word. But I think it should be doable. And we love to help, right? Again, we don't looking for any benefit. We love to see the algorithm in the real world.
Just one follow-up, what you could probably add to the research agenda is what Marcus showed in the prior session was that you might have height battles between an empty block and a valid block which has transactions. So it would also make sense, I would assume in the future, that if something like this occurs, that the block with the largest fees would be included.
Yes, or
it's not happens not so often, but it happens.
Yeah, or you can even see it like this. Like, let's say I want to help the propagation time of block, so I will intentionally create a small blocks, right? Because you want the other nodes to see your block faster. You can still get the optimal block for that a smaller block, right? Yes.
Yeah, because right now pools could intentionally set as empty blocks because they get faster propagation because it doesn't matter to them because they don't get the fees.
Yes.
So yeah.
Okay. And I guess I'm always happy to answer questions. Either drop me an email or my supervisor. We love to have chat. And sorry, one more thing. I know that the time is limited. We like optimization or program analysis problems, right? We like to see them from eyes, from a theoretical point of view, and we like to solve them. So if you have any problem that you think we can have a collaboration, we enjoyed our working with Cardano and Marcus. We love to help. So we did other things. It also benefits us. It helps us to get papers, right? This was published in IEEE blockchain. And it helps us to not just lost in our academic world, right? We will see some new problems, which is very nice. I see some point that we are trying to solve problems that they are not there. Even in this problem, you can see it a little bit. But whenever we have a better communication with community or industry, we get better problems. Okay, that's it. Thank you for listening.